and I'll fill y'all in a little bit on how things are with me. Um, I was telling Kira before the rest of you got here, my treatments last week went really, really well. I was just so pleased. I was afraid with the counts being as high as they were, I was going to have some adverse reactions. Didn't happen. The Thursday when I had the 10% dosage, I got really, really hot, which indicates to me the chemical was the monoclonal antibody was attacking those white cells like crazy, and just I ate ice for part of the day just to keep the heat down, and so I came out of that really well. Then Friday I went, and it was almost like it was just it wasn't nearly as it was a 90% dosage, but I didn't sense nearly the inner battle going on that we had before. So I was really, really pleased with how it went. However, I'm pretty sure the monoclonal antibody also knocked down my red cell counts, because today I am dragging like crazy. I was already really anemic, and now I'm even worse. So if I stop and have to drink some soda or something like that, it's just because I have almost no energy today whatsoever. So anyway, enough of that sad song. But anyway, we'll proceed with that. Now, the rest of the things that were going on, I think I told you about last week. My wife and I have to go back to our friend's apartment and clear out, hopefully the last that we'll have to clear out this afternoon after the differential equations class. We've got, and after that, hopefully everything will be taken care of. We had the memorial service yesterday. It was very good, but it was, it was draining, to say the least. And so it's just been a really emotional and a tough week. So it's slowly getting over with. So we got this one more thing to do today. Then hopefully after that, we'll be in better shape. So anyway, that's where things are there. And so hopefully by Wednesday, things will have settled out and I'll be back in kind of a groove. I feel like I've been out of the groove for about 2 weeks now, but hopefully we'll get back. So any questions, issues, problems on your part before we get going today? Okay. Last time, yes. Yes. Well, thank you so much. I'm feel like I'm on the mend, but it's just going to be, I think, a slow process. But thank you so much. I am convinced that things are just going to keep getting better from this point on. Now, I'm scheduled right now to have another um, um, treatment in a month. My guess is, or at least my hope is, that the counts they're going to find are so low I won't need it in another month. So, but if I do, but then it'll just be on a Friday. It won't be messing up the rest of the, I hope it'll be on a Friday, the rest of the week. So anyway, thank you though. All right, we just let Jesus in, so we got half the class here. Hopefully the others will be coming later. All right, so any other issues, problems, concerns that you want to address before we get started today? All right, we're in chapter 11, Vectors and the Geometry of Space. We're in section 11.4, and we're talking about the cross product of two vectors, okay, in space. Now, when we're talking about dot products, those can be in a plane or in space. It doesn't matter. But a cross product has to be three-dimensional, because what you have from a cross product, any two vectors that you're crossing, any two vectors are always going to define a plane. But when you cross them, you come out in the dimension perpendicular to both of those dimensions. So you're going to be in the plane. So here are the algebraic properties of the cross product. Sorry. All right. I just crammed down part of my lunch, so I'm a little choked up here. Sorry. Sorry. Let's let u, v, and w be vectors somewhere out here in space. Okay? Three-dimensional vectors. They have to be three-dimensional vectors. Let c be a scalar. Okay? Any number. Positive, negative, fraction, decimal, rational, irrational, any number. U, v, and w, vectors. Now, your cross product. U cross v is not the same as v cross u. It's exactly the opposite of v cross u. Now, I'm going to introduce this to you. They haven't done it yet, but I'm going to introduce to you now. If you have a vector u, let's say is going in that direction. Okay, I'm going to use my right hand. In that direction, okay? And vector v is going in this direction. Well, then if you point your fingers on your right hand in the direction of vector u, then bend them at the hand to be in the direction of vector v, then where your right thumb is pointing, that's going to be the direction of your cross product. So it's going to be perpendicular to the first vector, the second vector, to both of those vectors. So that's why it's got to be in space. Okay. Now let's say we started with vector v, okay, and crossed it with vector u, which I've got to turn around this way, cross it with u. Look at there. The right thumb is pointing in the opposite direction from what it was before. And that's what we mean. The u cross v is not commutative. It's anti-commutative. Okay? It's the opposite of v cross u. Absolute opposite. Okay. Now, here's the second of these algebraic properties. What do we have if we cross vector u with the sum of two vectors? Okay? Vector v is going somewhere, vector w is going somewhere. When you add those together, you get another vector in the plane with v and w. That produces a vector. Adding two vectors gives you a vector. And you cross that with then this third vector, u. U cross the sum of v plus w. Well, that's going to be the same as u cross v plus u cross w. So that's a straight distributive property. Okay, they didn't name it that way, but the cross products are anti-commutative, but they do distribute just like you would expect them to. U cross v plus w is the same as u cross v plus u cross w. Okay, no negatives in there, exactly like you expect. Now, here's the third one. This time we're going to distribute a scalar across the product of the cross product of two vectors. C times u cross v. Okay, well that could be either cu cross v, or you could do u cross cv. Either one. You can associate, well, distribute, I would say, the c to either one of the two vectors, but not to both, just to either one of them. So it's either cu cross v or u cross cv. Now, here's the next one, and this is that weird vector. Oh, whoa, here comes Laurent. So let me get Laurent admitted and marked on the roll book. So we're up to, okay, the top part of the alphabet started strong, but the bottom part has come roaring back, and now we have 3-2, the bottom part of the alphabet. So we need those three in the middle, and hopefully we will be in good shape. Okay, so welcome, Laurent. We're talking about the algebraic properties of the cross product. Okay, the next one, number 4, if you have some vector u, any old vector u, cross it with the zero vector, that weird zero vector. no magnitude, no direction, the zero vector, guess what? You got nothing, okay? That's the same as 0 cross u. This time that is commutative because that's neither positive or negative, it's 0. You get the 0 vector because remember the cross product produces a vector, not a scalar. So that is the 0 vector. Now, sort of surprisingly with that, u cross with itself is going to produce the 0 vector as well. Now here's why that. You have the vector u crossing with itself. Hey, it has nowhere to go. There's no bending of the fingers or anything like that. You produce the 0 vector. And basically any vectors that are parallel to each other, if you cross them, you get the 0 vector. Okay? Remember the dot product, two vectors that are perpendicular to each other, you dot those and you get the number 0 because the dot product produces a scalar quantity. Vector product produces a vector. A cross product produces a vector quantity. Okay, and then here comes another kind of weird combination. You start with vectors v and w, okay? Cross product between v and w. That's going to give you something perpendicular to both v and w. Dot that with u, and that gives you the same thing as u cross v dotted with w. Now that is not completely obvious why that would be true, but that is one of the interesting algebraic properties of the cross product. Okay, we'll be talking about that one a little bit later in more detail. So those are our 6 basic algebraic properties of the cross product. Number 1, cross products are not commutative, they're anti-commutative. Okay. Number 2, cross products do distribute the cross product across vector addition. Okay. Number 3, if you're distributing a scalar across a cross product, you can distribute it across either of the two vectors being crossed. Doesn't matter, just do it on one of them. A vector cross with the 0 vector is always going to be the 0 vector no matter which order you do it. That's the one time they are commutative. And then a vector cross with itself is always the 0 vector as well. And then that third one, sixth one, we'll talk about that a little bit more later. Okay. So let's move on to any questions on those properties. Okay, my clip keeps falling off my pocket, and I'm afraid it's going to mess up the either my hearing or the microphone, but hopefully we got it done. Okay, so let's move on to the next page. If I could get it to advance, we'll try. There we go. Those were algebraic properties of the cross product. Now we're going to hit some geometric properties of the cross product. And I've already sort of started on this one for you. Okay? So let's let, again, u and v be non-zero vectors in space. U here, v here, wherever. In space. Let theta be the angle between u and v, whatever that is, okay? A small angle, a wide angle, whatever. The angle between u and v. Now, the cross product of u and v, I've already suggested this before, u cross v is orthogonal. You could also think of it in terms of perpendicular or normal to both u and v. Okay, the cross product is always perpendicular to both of the two vectors. Now, if you recall back in the dot product, we had u dot v being magnitude of u times magnitude of v times the cosine of the angle in between. When we're talking about a cross product, now a dot product is going to produce a scalar quantity. Okay, so that's why magnitudes were fine. Here, a cross product produces a vector, so you have to have the magnitude of that cross product. To get a scalar quantity here is the magnitude of u times the magnitude of v times the sine of the angle in between. Okay, So these are scalar quantities here. Okay, look similar, but it's different from dot product. U cross V is equal to 0. Now we hit these before, okay, in some sense. If and only if U and V are scalar multiples of each other. Now back here we said U cross U is the 0 vector. Now we're saying if U and V are scalar multiples of each other, in other words, if they're going in the same direction, either exactly the same direction or exactly the opposite direction, either one of those, then their cross product is 0. Now, where does that come from? Think of this. If the theta is 0, then the cross product is going to be 0, because sine of 0 is 0. If the theta is pi, or 180 degrees, then sine of pi, or 180 degrees, is also 0. So therefore, U cross V is the 0 vector, because cross product is always a vector, if and only if U and V are scalar multiples of each other. They have to be either in the same line or exactly opposite in line. I mean, just collinear, either way. Now, this thing here, U cross V, the magnitude of U cross V, interesting. The area of a parallelogram having U and V as adjacent sides. That's what this thing is here. U cross V, the magnitude of U cross V is magnitude of U, magnitude of V times the sine of the angle in between. Now, if you think about that, that sort of makes sense, because magnitude of U, magnitude of V, okay, the sine of the angle in between would then be the component of one in the perpendicular direction of the other, and that gives you the area of a parallelogram. We'll hit that a little bit later. Okay, it's sort of hard to do that waving my arms. Okay, so here is the figure that kind of illustrates that. Both U cross V and V cross U are perpendicular to the plane determined by U and V. We already said that. U and V, any two vectors U and V, are going to define a plane, no matter where they are, defines a plane. The cross product of either U cross V or V cross U is always going to be perpendicular to whatever plane those two determine. One way to remember the orientation of the vectors U, V, and W, U and V and U cross V, is to compare them with the unit vectors X, Y, I, J, and K, and just remember, if you do them in that order, I, J, K, I cross J equal K, J cross K equal I, K cross I equal J. If you keep them in the order, I, J, K, and whichever, oh, here comes James. Let me get him in. Hold on just a moment. James is here. All right, bottom part of the alphabet is really surging now. We're missing Houston and Kyle. Now, Kyle may have a baseball game. I don't know if he does or not. I haven't heard from Houston. Okay. So anyway, James, we're in chapter 11. That's vectors in the geometry of space, section 11.4, the cross product of two vectors in space. We're on page 781, just about the middle of the page there. Okay. Now, cross product, U cross V, V cross U, any two vectors defines a plane. Now, the only exception to that, if those two vectors are collinear, either anti or exactly, they don't define a plane. Okay, and in that case, the cross product is 0. Okay, but any two vectors that are not collinear, they define a plane, and the cross product between those two vectors, whichever way you do it, is always going to be perpendicular to that plane. Of course, one goes in one direction, one goes in the other direction, because they're anti-commutative, we talked about before. Okay, one way to remember is this orientation of I, J, and K like we just talked about. So I cross J, point your right hand fingers in the direction of the positive x-axis, cross to positive y-axis, your right thumb is going to point upward in the positive z direction. Go the other way, start with J, the positive y-axis, cross that with K, the positive z-axis, and your right thumb is pointing in the direction of positive I. Okay, so if you keep the order going, I, J, K, and you cross them, I cross J is equal to K, J cross K is equal to I, and K cross I is equal to J. Always works that way. And this is called the right-handed system. Okay, now the three vectors u, v, and u cross v form a right-handed system, whereas the three vectors u, v, and v cross u form what they call a left-handed system. Now, I don't like to turn around and do that. I'm left-handed, and it would be fine to do, but just always think of it as a right-hand rule. And if you cross the other way, you get the opposite of that. Rather than thinking, oh, this is left hand, this is right hand, just remember, right-hand rule. That's what rules. Okay. Now, it won't advance, so let me click on it again. Here's example 2. Okay. Top of page 782. Find a unit vector that is orthogonal to both u, which is I minus 4j plus k, and v, which is 2i plus 3j. And you might say, wait a minute, didn't you say these have to be three-dimensional vectors? They are. It just happens that v has no component in the z direction, okay? But it's still a vector in space. It's just that it doesn't have a z component to it. It is a vector in space. This is a vector in space. So how are we going to find the unit vector that is orthogonal to both of those? Now, we have already shown how to do this. We did this last week. So let's do it again. We want a unit vector orthogonal to both u and v. So let's do the cross product of u cross v. Okay, and if you remember what that was, we treat it like a determinant. Okay, and this is the first time. Now, so those of you who are in linear algebra, you've already hit determinants. But if you're not, this is it. It's pretty straightforward. You always write down the unit vectors. I, j, if I could write, k. Now, I go on and, because I know this is the technique I'm going to use, I repeat I and j again. Okay. Now, this is not strictly a determinant because you don't take a determinant of a rectangular matrix. It has to be square, but it's producing the same effect. Okay, then you put the one that's listed first, which would be 1 minus 4, 1, and then repeat the first two again, 1 minus 4. Okay, and then the v, the one that's listed second, would be 2, 3, 0. 2, 3, 0, 0k, and then repeat 2 and 3. All right, then we do our down diagonal. That gives you 0i. Okay, then we do the next down diagonal, and that gives you a plus 2j, if you could read my writing, 2j. Okay, then do the third down diagonal, and that's 3k, plus 3k. Unit vectors, I usually put the house tops on. Okay, now I'm going to erase my construction lines just because they get a little messy and make it easier to read. All right, now I do my up diagonals. Okay, remember the up diagonals are always the negative of what they would be. So this would have been a -8, but you negate that, and that's a positive 8k. So we're going to add this 8k here. Okay, then the next up diagonal is going to be, it would have been a 3i, but because it's up diagonal, it's a minus 3i. I didn't leave enough room here, but I think we can manage. And then this one, of course, goes to 0. Okay, so what is our cross product? It is minus 3i plus 2j plus 11k. Now, have we done what they asked for? We have found a vector that is orthogonal to both u and v, but it's not a unit vector. How do we get it to be a unit vector? Same way we did before. You take that vector, minus 3i plus 2j plus 11k, and divide it by its magnitude. And what is its magnitude? The square root of the sum of the squares of the components. Minus 3 squared would be 9, plus 2 squared would be 4, plus 11 squared, 121. Big old number here. Okay, so this is going to be minus 3i plus 2j plus 11k divided by the square root of, well, 121 plus 9 is 130 plus 4, 134. Now you could leave it like that, but a lot of times they'll write it this way. Minus 3 over root 134. I prefer component notation, but I'll write it the way they had started the problem anyway. Plus 2 over root 134j plus 11 over root 134k. Let's see how the book did. Minus 3 over root 134i plus 2 over root 134j plus 11 over root 134k. Perfect. Okay, now I do not draw three-dimensional vectors well at all. So rather than well, actually they may show it. So let's just move on from here and let's see if they're going to show us how that looks. So I'm going to erase anyone need me to leave this longer? Any questions before I erase it? Okay. There's my pen. Okay. Now, how do we proceed? The cross product is orthogonal to both u and v. Okay, so that's what we're going to do, just like we did before. Put our unit vectors here, I, j, k, then put the components for vector u next, 1, negative 4, 1, and the components for v next, 2, 3, 0. Okay, now, when they do the cross product, they go through the long, what they call goodness gracious, I can't think of the term now. Multiplying, adding the cofactors. Okay, and that's one way to do it. Oh, they don't even show how they do it. They just did it. Okay, I thought they were going to show those. They just write them down. Okay, skipping steps like crazy. But that's the same thing we got. This vector here is orthogonal to that one and orthogonal to that one. Guaranteed. Okay, how could you check? Well, simply dot this vector with that one. That would be a minus 3 plus 8. No, minus 3 minus 8 plus 11. That adds to 0. Let's do this one. 2 times minus 3 is minus 6 plus 0. Yes, perpendicular to both of those. So real easy to check that in case you thought you made a mistake. Okay, now here is the vector u. That's I minus 4j plus k So I is in the x direction, 1 unit here in the x direction, that gives you that point. -4 in the j direction, there's -2, -4, so yep, you're right there on that plane, and +1 on the k direction, so go up 1 from that little cross mark there. Okay, now this is almost impossible to define completely, because I mean, you just have to visualize this. Okay, cross this with 2I, that's 2 in the x direction, that would be here, plus 3j, positive 3 would be here, so here's that vector here, but you don't go up or down at all because there is no k component, so you're doing this vector here, which has a slight incline, just a very slight incline, with the vector that's in the xy plane here, so you're going to have something that's slightly off from your k vector. I mean, yeah, the k vector, your z component here. Now, it looks like they really extended it a bit large, but that's what you get. And that u cross v is going to be this vector here. Okay, -3 to 11. -3 on x, that would be -2 here, -3 would be here. 2 in the y direction, +2 here, so there you are there, and now 11 up. That's 2, 4, 6, 8, 10, and half of that is 11. From this point, you go up. You see, that's raised about like this. This will be raised about like that same amount. So yeah, really hard to visualize, but that's what you got. Perpendicular to both. However, it's not a unit vector, obviously. Way, way longer than unit vector. So how do we make it unit vector? Divide by its magnitude. Because u cross v, the magnitude of that is the square root of the -3 squared, the square root of -3 squared plus 2 squared plus 11 squared. That's the square root of 134. The unit vector orthogonal to both u and v is then u cross v divided by the magnitude of u cross v, which is -1 over root 34. I mean -3 over root 34i plus 2 over root 34j plus 11 over root 134k. I was not saying 134, I should have been. All right, any questions on that? There's example 2. All right, now they're skipping example 3 completely, so let's back up 1 and do example 3. Okay, let's go to the whiteboard here. And let's see, I think I've got y'all pushed as far as I can to the right. Yeah, you're fine. Let me move this taskbar, which you can't see, as far out of the way as I can. Okay, and then I'm going to move my whiteboard in the opposite direction as far out of the way as I can. So I have maximum white space to work with. Okay, I think that has us done. Okay, so let's do example 3. The vertices of a quadrilateral are listed below. Show that the quadrilateral is a parallelogram and find its area. Wow. We aren't there yet, and they're already having us do this. Okay, we're going to come up with this in a little bit. So here's the vertices of a quadrilateral. 4 vertices. Vertex A, and this is a point now, not a vector, a point in space. 5, 2, 0. Now that happens to be in the xy plane. It doesn't have a z component. Okay, here's point B. It's 2, 6, 1. These are points now, coordinates of a point. 2, 6, 1. Here's point C. is 247. Yuck. 2, 4, 7. This weird board here does strange things sometimes. And D is another point, and this point is 506. Now that's a point in the XZ plane. Okay, no Y component. Okay. Now they tell you those are the vertices of a quadrilateral. Okay. Now what we don't know, it says to show. Okay, time out just a moment. What do we mean by quadrilateral? Quadrilateral means four-sided figure. That's all it means, four-sided figure. Okay, these are 4 points in space, and since no two of these are collinear with no three of them are collinear, this does form a four-sided figure in space. Okay, now what we're trying to show is these are a parallelogram. Okay, and also find its area. Now, how could you show that this is a parallelogram? Well, that means the two of the opposite sides have to be parallel to each other, and the other two opposite sides have to be parallel to each other. Well, what does that entail? That means that their cross products must be 0. For them to be parallel to each other, the cross products must be 0. So let's just start comparing the cross products of these, the vectors represented by AB, AC, and AD, and see if any two of those are parallel with each other. So let's first do the vector AB. Okay, initial point A, terminal point V. Okay, that would be the vector now. 2 minus 5 is a minus 3. 6 minus 2 would be a 4. And 1 minus 0 would be a 1. Okay, now let's do another one. AC, vector AC would be 2 minus 5 is a negative 3. 4 minus 2 is a 2. And 7 minus 0 is a 7. Okay, let's do vector AD. Initial point A, terminal point D. Okay, 5 minus 5 is 0. You see what we're doing here? 0 minus 2 is a negative 2, and 6 minus 0 is a 6. Okay. Now, we'll probably need at least one more, maybe two more. So let's do vector BC. And vector BC would be 2 minus 2 is 0. 4 minus 6 is negative 2. And 7 minus 1 is 6. Hold a moment here, folks. It's pretty obvious to me these two are identical vectors, which means they aren't coming from the same place, but they have identically the same components, so therefore they must be parallel to each other. Okay, the last one we'll consider is CD. Okay, vector CD is going to be 5 minus 2 is 3, 0 minus 4 is a negative 4, and 6 minus 7 is a minus 1. Uh-oh, look at that one. This is exactly opposite in direction of this one. Negative 3, 4, 1. This is 3, negative 4, 1. They're in the same, they're parallel to each other, just going opposite directions. So therefore, these two are parallel to each other. So if these two are parallel to each other, those two are parallel to each other, different points, then they must be form a parallelogram. They're exactly the same length and parallel to each other. So they are a parallelogram. That's all you have to show. Okay? We didn't have to do a cross product at all. We could, but we didn't have to. Okay? Now, it says show that the quadrilateral is a parallelogram and find its area. Okay. Now what you have to do now is go back to the previous page, 781, and we have number 4 there in geometric properties of the cross product. We have number 4, that the magnitude of the cross product of two vectors is the area of the parallelogram having those as adjacent sides. So we know that this side is adjacent to this side because they have the point B's in common. This is one, that's another. So all we have to do here is do the magnitude of the cross product. Oh, whoa, here's Houston. Good deal. Okay, so Houston is here. If I could find my pen, we're down to just one person missing. And that's Kyle, and he may be at a baseball game. So I know they're playing now, so that may be where he is. Okay, Houston, if you can hear me yet, we're in Chapter 11, Vectors in the Geometry of Space, in Section 11.4, the cross product of two vectors in space, and we're doing the Example 3, bottom half of page 782, they gave us the vertices, points of a quadrilateral. Okay, here they were, this point, that point, that point, and that point. Okay, we determined what vectors were formed by AB, AC, and AD, and BC and BD, and we sure enough found out that these two are anti-parallel to each other but in the same direction. These two are exactly the same. They are parallel to each other, exactly the same direction. So any two opposite sides, both sides being parallel, it's got to be a parallelogram. So we've done the first part of the problem. Now we're trying to find the area of the parallelogram. And what we learned on the previous page in the geometric properties of cross products on page 781, that the magnitude of, and they say U cross V. Well, our U here, let's call it AB, cross with, not CD, because you know those are in the same direction, but BC. Okay, they have one point in common, so they must intersect, and that would be cross BC. That will give you the area of that parallelogram. Well, what is that? That's our good old, sort of like a determinant, I, J, K, and then I like to just repeat the first two, I, J, and this isn't technically a determinant anymore, but we're treating it like one. This will be a -3, 4, 1. Those are the components of this one. And then repeat the first two, -3, 4. Cross it with BC, the other one, 0, -2, 6. 0, -2. Repeat the first two again. Now let's do our down diagonals. This would be 24I, pretty big number there, 24I. This will be 0J, and this will be plus 6K. Okay, now we're going to do our up diagonals. I didn't draw that third one because it was pretty easy to see. So I'm so sorry. As I was telling the others earlier, I'm just completely out of energy. Before my treatments, which went really well Thursday and Friday of last week, before that, well, I was very anemic, and the treatments usually drive down the red blood cells. They wipe out lots of white cells, which is what they were supposed to do, but they also sort of knock down the reds as well. So I'm even more anemic now, but I feel so much better because the white counts are down, but the reds are down too. So sorry about this. Hold on just a minute. Anything to boost a little bit of energy here. Okay. So what I was doing here, we did the cross product of these two, and we got the down diagonals here. Let's deal with the up diagonals now. Okay. Well, the first up diagonal is going to be a 0. The next up diagonal would have been a minus 2i, except since it's up diagonal, that's a plus 2i. And the third up diagonal would have been a minus 18j, but because it's up diagonal, it becomes a plus 18j. And then when you combine those together, that's pretty ugly, the writing. I'm sorry about that. The pen just does strange things. This is 26i plus 18j plus 6k. Now, this really gets to be interesting. That's the cross product of those two things. We now want to take the magnitude of that cross product, which is the magnitude of this thing, and boy does that ever give us some big numbers. Okay, so this is going to be the square root of 26 squared plus 18 squared plus 6 squared is 36. Okay, so this is time for the calculator. I don't do that big of squares in my head. Okay, 36 I can handle, but the other. Okay. All right, let's go to my calculator mode. And that will be 26. Whoops, I'm going to turn it sideways so I can do scientific notation. I mean, scientific calculator. 26 squared plus 18 squared plus, wow, 36 equal, that gives me 1036, and now I want to take a square root of that, and that gives me something on the order of 32.2 approximately. I think I'll just be happy with something pretty close to 32. Okay, so if I can find my pen again, this is going to be something on the order of fairly close to 32 square units, whatever they are. They did 32.19, which is what I got too. I would have said 32.187. It doesn't matter. Awfully close to 32. All right. Any questions on that? That's using that fourth property of your geometric property of cross products. All right. Now, that being done, let's move on back to our PowerPoint. Any questions before we leave this? Okay, let's go back to the PowerPoint. That's 11.4. And I think we're ready for Oh, I was wondering why it went way back there. I have to resume slideshow here. Okay. Now, top of page 783. In physics, the cross product can be used to measure torque. That's the moment m of a force about a point P. That's how we define torque. As shown in this figure here, relatively good figure here. If the point of application of the force is Q, then the moment of F, that force F, about that point P is, and that capital M stands for moment. Bolded because it is a vector quantity. Okay, so that moment, capital M, is equal to the vector from P to Q, okay, cross the force. Okay, now let's think about that for just a moment here. Okay, force is in that direction, cross the, well, I'm sorry, the displacement, I'm sorry, PQ, that's the one that comes first. PQ is coming, I can't get my hand to twist around there, is coming like this. Cross that with F and you've got the right hand thumb going up. I almost break my wrist trying to get those things to do. Okay, the magnitude of the moment m measures the tendency of the vector PQ to rotate counterclockwise using right hand rule about the axis directed along the vector m. Vector m is always going to be perpendicular to both your displacement P to Q and the force. Now, they make it look like this is a right angle here. It doesn't have to be. Any angle other than 0 or 180, because they would give you 0, okay? But any angle here, acute angle, obtuse angle, it doesn't matter as long as they're not collinear. So that's your moment m, is the vector PQ from the origin to Q. That's the how far you are from the point Q to where you're exerting the force, cross that with the amount of the force. And by the way, this is in this is a dimensioned quantity, like possibly feet, like possibly meters or something like that. This is a force which is could be pounds, it could be newtons. Well, if that is foot pounds, that sounds like a work unit. It's not a work unit, it's a torque unit. Has the same units as work, but it's a vector quantity. Torque is a vector quantity, work is a scalar quantity. Okay? Or if you did it newtons here times meters here, that would be Newton meter, which normally we would call a joule, which is a work quantity, but not if it's a torque. We would call it a Newton meter, vector quantity. But this is math course, they don't pay that much attention to units. All right. Now, they skipped example 4. So let's go back and do example 4. Any questions before I leave this? Okay. Let me clear my screen here and let's do example 4. It's hard for me to read, so I'm going to have to set this in my lap here. A vertical force, one going straight up and down, of 50 pounds is applied to the end of a 1-foot lever that is attached to an axle at a point P. Okay, is that enough? Okay. Find the moment of the force about that point when the theta is 60 degrees. So let me show you the figures, hopefully, so I won't have to draw it. Okay. If you got your book open, you can already see it. Okay. Let's see if I can get this to show. Okay. There is the, I think they said 1 meter lever, at an angle of 60 degrees with the horizontal, and the force F is pointing straight down the parallel. Oh, here's Houston. I thought he's already been here, so I was thinking Cal was coming in, but that's not Cal, it's Houston. So let me admit him in rather than just talk about it. So Houston's back. Okay. So that's your situation here. Vertical force 50 pounds supplied at the end of a 1-foot lever that is attached, and these will be in foot-pounds by the way, at a point P shown at the origin here. Find the moment of that force about the point P when the angle is at 60 degrees. Okay, now all that being said, I don't know if I need to draw the picture or not. Hopefully not. You've seen it in the book. But your moment, capital M, which is a vector quantity, is equal to the PQ, that's your displacement from the origin, cross with the force. Okay, let me see if I can get the pen to show up, the force. Okay, now this vector PQ, they told us was a 1-foot lever, so its magnitude is 1 foot. Okay, so magnitude of PQ is equal to 1 foot. Okay, the magnitude of the F here also a vector, and they said that was 50 pounds magnitude. Okay, now what they want to know is find the moment of that force about the point P when that angle is 60 degrees. Well, if you remember, one of our definitions of cross product was magnitude of the first vector PQ times the magnitude of the second vector F times the sine of the angle in between, and the angle in between they told us was 60 degrees. Okay, but it's got to have a direction with it. The direction has to be perpendicular to the two of those. Okay, now that would give you the magnitude of M. Is that what they're asking for? No, they're asking for the moment. Okay, so what we're going to have to do then is, rather than doing it this way, we're going to have to break this into components. Okay, now this component here, PQ, is, I almost have to draw the figure here. Sorry about that for my sake. Okay, there's the X, there's the Y, there's the Z. Okay, this PQ is 1 foot, and it's perpendicular, 60 degrees up from here. So let me sort of try to draw it. That's not really, it doesn't look like 60. Let's just imagine that's 60 degrees. Okay, and that's your PQ. PQ. Okay, cross that with your force vector, which is 50 pounds downward. Okay, and that's going to give you a vector, which is, that's going to be the moment, and all right, and I didn't realize it, but they were drawing that as if that's in the YZ plane. Now here's the x-axis, this is the y-axis, and this is the z-axis. So what we have to do is split this vector here in the YZ plane here. That would be 0 on x, okay? In the y direction, since this is 60 degrees here, and remember this is 50 pounds downward, and this is 1 foot this way. Okay. The component in the x direction is 0. In the y direction, if that's 60 degrees, that is going to be the cosine of 60. What's the cosine of 60? 1/2. So that would be 1/2 in the j direction. J direction is in the y direction. Plus, and in the vertical direction here, that would be the sine of 60 degrees, which is the square root of 3 over 2 in the k direction. Okay, so that's the component of your displacement vector where we had it. Okay, your force vector here is going to be minus 50 j, because, no, I'm sorry, k, minus 50 k, straight downhill, directly negative. Okay, so what we've got to do to find the moment is your good old I, J, K, I, that's an I, J. Okay, and then this I, the PQ here was 1/2. No, it was 0 there. Sorry about that. That's the 0 there. 0 I, 1/2 j, and it's square root of 3 over 2 k, and then repeat the 0 and the 1/2. Okay, now do the F component, and that's simply 0I, 0j, 50, minus 50, minus 50, k, 0, 0. All right. Now, this is not too bad. I, j, k going that way, 0. J this way, 0. This way, 0. Nothing in from those at all. So let me erase those construction lines so I'll be better able to see what's going on here. Okay, the up diagonal, 0, 0. Wait a minute here, folks. There's something wrong with this picture. Okay. Oh, I see. I went down wrong. Sorry about that. I read that to be a 0 and it's a negative 50. So this one down here is minus 25. Minus 25i. Sorry about that. And then this was a 0, that was a 0, that's a 0, and that's a 0, and that's a 0. So minus 25i is the moment. Okay? In the negative direction, negative I. Now, that's not really clear here, but that would be going back this way in that direction. There's your moment I. Negative in the x direction, no component in the y, no component in the z. And that makes sense because they pivoted around that point there, so it will be negative 25i. Sorry about that. I lost my minus 5 there. Okay. And they said find the moment of the force about that. but then they gave the answer as the magnitude of the moment. The moment is actually minus 25i, not 25. Okay. Now, any questions before we leave this? Okay. I'm trying to find my pen. Where is it? There it is. Okay. So let's go back to our PowerPoint 11.4. Okay, excuse me just another moment, folks. Sorry about this. Have to stop periodically and boost the energy level a little bit. Okay, so let's go back to our slideshow here. And this is so aggravating. There we go. All right. Now we're moving to the bottom half of page 783, the triple scalar product. Now, what do we mean by a triple scalar product? If you remember back, the algebraic property of a cross product that we did a couple pages ago, okay, there's your triple scalar product. For vectors u, v, and w in space, the dot product of u and the cross product of vw, v cross w, because it is a dot product ultimately, v cross w is a vector, okay, but that's a vector dotted with another vector that's going to be a scalar number. And they call this the triple scalar product, okay? And here's what theorem 11.9 says. For u equal u1i plus u2j plus u3k, I would have liked to have written that in just component notation, u1, u2, u3. V, v1i plus v2j plus v3k, v1, v2, v3. W, w1i plus w2j plus w3k, or scalar vector components w1, comma, w2, comma, w3. The triple scalar product is, now remember, we have to write it this way, the dot product in front times the cross product here, okay? And if you think back, they said that's the same as u cross v dot w. So it would work that way as well, but they're just defining it this way here. Then this triple scalar product, because this is a scalar, not a vector anymore, so you don't have the I, J, and K there, you just put the three components just like you see them as a matrix, a determinant of a matrix, and I can't get my pen to show up. Where in the world is it? Can anyone see the pen? There it is, way up there. Okay, you put the, where is it? Come on, where are you? There we are. Okay, there we go. U1, U2, U3, V1, V2, V3, W1, W2, W3. These are all numbers now, no vectors in them, because this is a dot product, this is going to be a scalar. And we do it just like we did before, expand it, repeat the first two columns, then do your down diagonals positive, up diagonals negative, and add them together. Okay, you just don't have any vector components anymore. Okay, so let's watch them do that. If the vectors u, v, and w do not lie in the same plane, now if they are in the same plane, if all three of those vectors are in the same plane, okay, they don't show it well here. If they're in the same plane, then the dot product, let's say here is your v cross w down here. If the u was also in that plane down here, then they're going to be v cross w would be perpendicular to both of those, and that would have to be perpendicular to u, and that would be 0. So if they are in the same plane, it's 0. Okay, so if the vectors U, V, and W do not lie in the same plane, okay, then the triple scalar product U dot V cross W can be used to determine the volume of the parallelepiped, okay? That's this volume of this six-sided figure here. It's a polyhedron, a multi-sided figure, happens to be six-sided figure. All of the faces are parallelograms, okay? With U, V, and W as adjacent edges. Here's the U here, the V here, the W there, all adjacent to one another. Any two of those define a plane, okay? And they're not all coplanar, okay? They have to be three different planes, okay? Then this gives you the volume of that parallelepiped, okay? Now, the base here, if you remember, I don't know if we really didn't do this, but it's true. The projection of U onto V cross W, which is exactly what this thing is. Projection of the dot product here. U onto the vector V cross W. The area of the base was simply the V cross W. Remember, the area of a parallelogram is the magnitude of V cross W, okay? Take that and dot that with the length of U, and that gives you then the volume of that parallelepiped, okay? Now, okay, this is theorem 1110. We just did 11.9. Flip the page. 1110, top of page 784. The geometric property of this triple scalar product. The volume V of a parallelepiped with vectors U, V, and W as adjacent edges is the absolute value. That's what the single bars stand for, not magnitude. It's already a scalar, but that scalar could have been negative. Volumes are never negative, so it's the absolute value of that triple scalar product, U dot V cross W. Okay, remember how we get it? U on the top line, V on the middle line, W on the components, and then do the determinant. Okay, so here's example 5, last example in this section. Find the volume of the parallelepiped shown in this figure, 1142, having U is 3I minus 5J plus K. So 3I, that would be in this direction here, 1, 2, 3, 3I minus 5J, that would be back here somewhere, okay, minus 1, 2, 3, 4, 5, okay, so you're back here, and then up K. Now that looks like it's a bit high, but I guess that's correct, okay. V is 2J plus minus 2K, so this is in the going blank in my mind, the YZ plane. Now this is hard to see here. You're not anywhere in the x-axis here, it's strictly in the YZ plane, 0, 2, minus 2, okay? And then this one is 3I plus J plus K, so it's 3I this way plus J, which is 1 unit this way, and then up 1 unit there. So this is a really hard thing to visualize here, okay? That first component is the one that you go across here and up there, up 1. This one is only in the YZ plane here, plus 2 in the Y, and this just doesn't look at all right. Plus 2 in Y, minus 2 in Z. So it is right, but it looks really weird. And then the third component is 3 on the X, which is 1, 2, 3, plus 1 on J this way, and up 1 here. Okay, that looks way too short, but that's what we got. Okay, so find the volume. Well, the volume is simply V is equal to the absolute value R, and I'm going to put the determinant there, and you just put the U. 3 minus 5, 1, and just repeat the first two, 3 minus 5. Then the second vector, 0 in I, 2 in J, minus 2 in K, and then repeat the first two, 0, 2. And then the third one is 3 in the I direction, 1 in the J, 1 in the K, and repeat the first two, 3, I. 3, 1, sorry about that. Okay, then sort of do like a determinant there, and this time I'll try to get the numbers right. Coming down this way, that would be 6 plus 30, that's plus 10 times 3 is 30, plus 30, plus 0, that one was easy. Okay, now I'm going to erase my construction line just so it'll be easier to see what comes next. Okay, and that would be the up diagonal here is a minus 6. So those two go out. Okay, the next up diagonal is a plus 6 because it's a minus 6 here, but because it's going upward, so that's a plus 6 there, and then the third one is 0. So what we've got here is 36. Okay, that's the volume of that parallelepiped. Okay, 36. Now, and that's what they got in the book. So let's watch how they did that. I'm going to erase my scratch here. Okay. By the theorem, we have that the volume is the absolute value of U dotted with V cross W. Our U was top row 3 minus 5, 1. Second row 0, 2, minus 2. Third row, 3, 1, 1. Okay, and when they expand it by cofactors, you can do it that way. It's just so much easier doing it, expanding the first two columns. But you see, when they did it, they get 36, just like we did. Okay, now a natural consequence, though, of that theorem, 1110, is that the volume of a parallelepiped is 0 if and only if the three vectors are coplanar. No other way that can be a 0 triple product, okay? Triple scalar product. That is, if the vector u, which is u1, u2, u3, v, v1, v2, and v3, w, w1, w2, and w3 have the same initial point. They lie, okay, or when the vectors have the same initial point, okay, they lie in the same plane if and only if this u1, u2, u3, v1, v2, v3, w1, w2, w3, if that determinant there gives you 0. That's the only way this will have a I can't think how to say it. The volume would be 0 if they're all in the same plane. And I swear, I'm so tired. Whoops. Hold on just a minute. Sorry. Okay. Let me get a little water or two. Okay, sorry folks, I'm just running out of energy. Now, I didn't mean to advance that, so let's go back. All right, so that's it. Okay, now based on that, that finishes 11.4. Homework exercises here. Always look at your concept check. Okay, think through those. There's only two things there. If there is anything that is in calcchat.com, it would probably only be number 1. I don't know if they even list either one of them. But then the homework exercises, either 3 or 5, both at CalcChat, 7 or 9, both at CalcChat, 7's at CalcView, 11 or 13, both at CalcChat, 15 or 17, both at CalcChat with 15 at CalcView, 19 or 21, both at CalcChat, 23s at both CalcChat and CalcView, 25s at CalcChat only, and then any of the odds are either 27 or 29. They should both be at CalcChat. 31 or 33 both should be at CalcChat. 31's at CalcView. 35's both at CalcChat and at CalcView. 37 should be at CalcChat. 39 or 41 should both be at CalcChat. And then you have some true false. 43 or 45 should be at CalcChat. 47 to 51 should be at CalcChat. And 53 or 55 should be at CalcChat. Okay, so that finishes 11.4. And I keep knocking this thing off of my pocket. I hate that. Okay, so now we can move on. Any questions on 11.4? Okay, I was going to say it's like 11.5. All right, so let's move on to, and we'll discard that and end that and go to 11.5. Okay. Now, can you see, you should be able to, but I can't tell from here, can you see my PowerPoint? Okay. Okay, I'm trying to move the taskbar out of the way so we can read it better. Okay, let's go from current slide then. Okay. Whew, goodness, I'm tired. All right, 11.5, chapter 11, still vectors in the geometry of space. 11.5 is lines and planes in space. Okay, now our objectives here are to write a set of parametric equations for a line in space. Okay, now in a plane we're used to dealing with lines, but in space it's a little more complicated. Not badly, but a little bit. We'll write a linear equation to represent a plane in space. Okay, so let's catch the difference here. If you have a set of parametric equations, that defines a single line in space. A linear equation, a single linear equation, represents a plane in space. Now notice this, parametric equations for a line in space. Now they don't say it, but this is also linear. This is linear. Okay, anytime things are linear, you have either straight lines or flat planes. No curvature either in the line or in the plane. That wouldn't be a plane if it's curved. Okay, now we'll then sketch a plane given a linear equation. Ugh. Sketching planes on a two-dimensional space is not an easy thing to do, but we'll do that. And we'll find the distances between points, planes, and lines in space. Difference between 2 points, the distance between 2 lines, and the difference between 2 planes. Okay, we'll try to do all 3 of those. So let's start with lines in space, the first subtopic in this section. Now, in this figure, 11.43, consider the line L through the point P, which is x1, y1, z1. There it is, right there. That point right there, x1, y1, z1. Okay, x1 is how far you are on the x-axis, y1 looks like a negative value in the y direction, z1 looks like a positive value in the z direction. Okay, now that is, consider a line that's going through that point, but it has to be parallel to some other vector v, which is, this vector has components a, b, c. Okay, what does that mean? Okay, that means if you go anywhere in the x direction, that's going to be a units this way, b units this way, and c units up. Okay, so there's your vector that is right here, a units in this direction, b units in that direction, c units up, that vector, and we want to draw a line, consider a line that goes through this point but is parallel to that vector there. Okay, now this vector v is called the direction vector for that line L. That gives you the direction of the line. Doesn't tell you anything about magnitude, but it does give you the direction. The A, B, and C are called your direction numbers. They're the component of that vector v. Okay, components. Those are called the direction numbers. One way of describing that line L is to say it consists of all the points Q of x, y, z. These are points Q of x, y, z. They can be points back here, points here, points here, anywhere on that line, points for which the vector PQ is parallel to that vector v. Okay, that's what we mean. Now, what does that imply for you? That means that this unknown component here, coordinate here, x, has to be x minus x1 has to be some multiple of this number a. And y minus y1 must be the same multiple of that number b, and z minus z1 has to be the same multiple of this number c. Okay, because these two, this point here, x minus x1 must be parallel to a, y minus y1 must be parallel to b, z minus z1 must be, in the same direction as c. Okay, and if all three of those have to be true, that means the ratio of them must be the same. So that means that PQ, that from the initial point P, x1, y1, z1, to Q, which is any point x, y, z, is a scalar multiple of V, and you can write that PQ as some parameter T times V. Okay, parametric, just multiply that scalar number times V, where T is a scalar, any real number in the world. So this is saying that PQ, that line going from P to Q, is final minus initial, x minus x1, comma y minus y1, comma z minus z1, has to be that same ratio times those direction numbers, a, b, and c. AT plus BT, AT comma BT comma CT, or T times that vector V. By equating the corresponding components, you can obtain the parametric equations for a line in space. And that's exactly this. X is equal to x1 plus AT, y is equal to y1 plus BT, z is equal to z1 plus CT. Those are your parametric equations. So that theorem, theorem 11.11, says the parametric equations for a line in space, a line L parallel to some vector V, which has these as your direction numbers, A, B, and C, gives the direction the x-axis, y-axis, z-axis, and passing through the point P, x1, y1, z1 is represented by these parametric equations, x equal x1 plus at, y is equal to y1 plus bt, z is equal to z1 plus ct, where x1, y1, z1 are your point that you're coming from, and then the at, bt, and ct are your multiples, constant multiple of those direction numbers. If the direction numbers a, b, and c are all non-zero, none of them can be zero, then you can eliminate the parameter t in the parametric equation to obtain the symmetric equations. These are called parametric equations. These are called symmetric equations. And what you do is do this one, x minus x1 divided by a, y minus y1 divided by b, z minus z1 divided by c. All those are equal to t, so x minus x1 over a has to equal y minus y1 over b, has to equal z minus z1 over c. Those are your symmetric equations. No t involved with them. You've eliminated the t. Okay. Now, somewhat useful. Usually these are the ones we use a bit more, but we'll see where they both come in handy. So here's example 1, bottom of page 787. How are we doing on time? 3 minutes. Oh, sorry about this. Find the parametric and symmetric equations of the line L that passes through the point 1, negative 2, 4, and is parallel to this vector v, 2, 4, negative 4. Okay? So, what we have, the parametric equations would be this. Okay? X is equal to 1 plus 2t, y is equal to 4 minus 2t, and z is equal to minus 4 plus 4t. There are your parametric equations. Okay? Let's see if that's what the book got. I hope I did it right. X is equal to 1 plus 2t, y is equal to negative 2. Oh, I did them backwards. I'm sorry. That one I was in a hurry. Sorry about that. I got these two numbers backwards. Let me make sure I didn't get any others backwards. 1 plus 2t, negative 2 plus 4t, and 4, yeah, I got that one backward too, 4 minus 4t. Sorry about that. Goodness gracious, I can't believe how bizarre that came out, because it's just a simple process of plugging and chugging. Okay, let me make sure I got them right now. 1 plus 2t, negative 2 plus 4t, 4 minus 4t. Got it. Okay, what would be your symmetric equations? Okay, solve each of these for t, and this would be x minus 1 over 2 must equal y plus 2 over 4, and that must be equal to z minus 4 over a negative 4, which I think I would have preferred to write this way, 1 minus z. Let's make it 4 minus z over 4. Either way would do, okay? And they left it as z minus 4 over minus 4. Perfectly fine. So there's example 1, okay? Find the set of parametric equations for the line. Use the coordinates. x1 is 1, y1 is negative 2, z1 is 4. The direction numbers 2, 4, negative 4. And this would be x equal 1 plus 2t, y is equal to negative 2 plus 4t, z is equal to 4 minus 4t. And then to get your symmetric equations, these are all non-zero. If any of those were 0, Can't do it, okay? You cannot do it because then you would be dividing by a 0 somewhere. So these are all non-zero, so you can do this. This would be x minus 1 over 2, y plus 2 over 4, and z minus 4 over negative 4. There's your symmetric equations. But all three of those, A, B, and C, none of them can be 0. All right. And I think we're going to have to stop there because we just ran out of time. Okay. Now, we still have example 2 to go. So let me put a mark here. We'll start with example 2 next time. And let's see how many homework exercises. I doubt if it'll be too many. This is 11.5. I think you can do number 5 and any of the odds 7 through 11. Number 5 should be at Calc Chat. 7 through 11 should all be at Calc Chat. 9 should be at Calc View. Okay. I believe you can do 13 or 15. They're both at Calc Chat. 15 should be at Calc View. And I think you can do any of the odds 17 to 23. They should all be at Calc Chat. Okay. And I think the next one we'll just wait and do after we cover example 2. Any questions? All right, good deal, folks. Sorry I'm so out of energy, but any questions on anything we've done 11.4 or 11.5? Okay, now we're going to proceed with 11.5 next time. I doubt if we'll finish. We'll hopefully finish 11.5 and get into 11.6, but I don't think we'll finish 11.6. So I'm guessing right now the next test, chapter 11 test, will come middle of next week probably. Probably after Monday's class, but we'll have to see. So folks, try to get your, I know most of you have turned in test 1. If you haven't, then get that in and also get test 2, wrapping that up this weekend if possible. Okay? Any questions? Okay, I'm going to stop the sharing then. Sick and tired of sharing. Y'all be careful, be safe, and we'll see you on Wednesday. Okay? Take care. Bye-bye.